Welcome back to ECE 320A. In this particular video in Unit 7, we want to look at finding a couple of different transfer functions associated with a single electric circuit. The electric circuit that what I want to look at is a series RLC circuit. I've identified a voltage source that's going to be driving that circuit. We have a resistor, an inductor, and a capacitor. I've identified a current. I've identified a voltage across the capacitor. You could define voltages across the resistor. You could define voltages across the inductor. The current's the same through all three, so we're probably not going to have any different current in this series RLC circuit. To find the transfer function, we want to be doing the analysis in the frequency domain or with an S-domain equivalent circuit. And the S-domain equivalent circuit, when we're dealing with a transfer function, we do not have to worry about initial conditions. So since we're trying to find a transfer function, we can neglect the initial conditions. We're not interested in the transient behavior or any kind of transient response. We're actually interested in how does this system behave if we excite it with an input, and that being the case, we can then find that system's behavior by looking at the transfer function without respect to any initial conditions. If we now put this circuit into the S domain, we now simply replace the R's, the L's, and the C's with their respective impedances. V sub G will leave as just an unknown, an independent voltage, which will just be capital V sub G of S in the S domain circuit. In that thinking, then, we have our source, V sub G of S, polarity in the same direction that we started with in our time domain circuit. We have a resistor in series with an inductor, in series with a capacitor, and each of those circuit elements has their respective impedance values. The resistor comes over, as are the inductor, SL, and the capacitor, 1 over SC. We might be interested in the current in that series circuit. Maybe we are interested in the voltage across the capacitor. As I said, we want to identify a couple of different transfer functions associated with the same circuit so that you get comfortable with this idea that you can have multiple transfer functions coming from or associated with the same electrical circuit. Suppose somebody now wants to find the current. Now the beauty of the S domain is that now we can apply our analysis that we learned very early on in electrical engineering, and that was to just maybe have purely resistive circuits and everything was algebra. Now we can do the same thing, except now these are more than just resistors. We have generalized resistors, which are impedances with an impedance of inductors with an impedance of SL, and capacitors with an impedance of 1 over SC. That being said, if somebody now wants to find an equation for the series current I of S, we now just have one source that drives that, V sub G of S, and we can divide that by the total impedance in that series circuit, which in this case is just now the sum of these three impedances, R plus SL plus 1 over SC, and that's now the relationship between the applied voltage, V sub G of S, and a resulting output, which might be the circuit's current, that's the series current, I of S. Suppose we now want the transfer function, H sub 1 of S, to be defined as the output is going to be our current in that circuit, and the input is V sub G of S. There are all sorts of ways to now find this. We could simply take this expression, this relationship, this equation, and divide both sides by capital V sub g of s, and we end up with I over V sub g equaling now just 1 over R plus SL plus 1 over SC. Or we could, in fact, just say, oh, I of S over V sub g of S, but we have I of S, that's now V sub g over R plus SL plus 1 over SC, and divide that by V sub g of S, so that these V sub g's cancel, and again, H sub 1 of S becomes equal to 1 over R plus SL plus 1 over SC, just as we had before, by dividing through both sides in that highlighted yellow by V sub g of S. Either way, we now have H sub 1 of S as a ratio of ratios, in fact, and we don't really want that. We really just want polynomials in the numerator and polynomials in the denominator, and we can find that here by putting the denominator terms over a common denominator, which is SC, so that we now have SRC plus S squared LC plus 1. All of that is in the denominator, but we now have a term in the denominator of our denominator, or we could multiply by 1, which is SC over SC, and H sub 1 of S now becomes SC over S squared LC, and the convention usually is to go ahead and put the highest power of S first, plus S RC plus 1, and that now gives us one transfer function associated with that RLC circuit, and this one transfer function is associated with an input V sub g and an output I, the current in that circuit. Suppose that now somebody said, well, I was really interested in the transfer function between V sub g and the capacitor's voltage V sub c of S. Not a problem. We already know I. We can find V sub c by a clean or a quick Ohm's law generalized to be in terms of impedances. So that now H sub 2 of S, suppose now we want that to be the transfer function between the applied voltage V sub g of S, which is downstairs, that's the Laplace transform of our input, and upstairs in the numerator is the Laplace transform of our output. Well, V sub c of S is just the impedance of our capacitor times the current flowing through that circuit, or this is now 1 over SC times V sub g of S over R plus SL plus 1 over SC, going back in terms of what I was expressed as in terms of V sub g and the impedances. If we multiply the denominator through all of those terms through by SC, we'll actually cancel that third 1 over SC, or the SC in the 1 over SC expression, and we're left now with V sub g of S over SRC plus S squared LC plus 1, and that's now equal to V sub c of S. Again, as I suggested before, when I highlighted something in yellow, I could now say, oh, to find H sub 2 of S, which I wanted that to be the transfer function between the applied voltage V sub g and the output voltage V sub c, I could divide both sides of that yellow highlight by V sub g of S and end up with 1 over S squared LC plus S RC plus 1. And that's now the transfer function between the voltage source, V sub G, and the capacitor's voltage, V sub C. And what you might do is start looking at anything in common between this transfer function of that circuit and this transfer function of that circuit. And I hope that you see that the denominator is exactly the same in both, because they both have the same characteristic behavior. They're both arising from the same exact circuit. So you would expect the transfer functions to have some similar characteristics. And that's what I want to finish this particular video with, the following statement. The characteristic polynomial, you may hear people refer to that, and I will be referring to that throughout the remainder of the course. The characteristic polynomial, what characterizes the behavior of a system or a circuit, is actually equal to the denominator polynomial. In this particular circuit, then, the characteristic polynomial is right there. It's S squared LC plus SRC plus 1. And that characteristic polynomial, which is the denominator polynomial, we just determined is the same in both transfer functions, h sub 1 of s and h sub 2 of s. And the reason for that is because they are containing the characteristic behavior of your circuit. And that's then contained in the denominator polynomial. And remember, the roots of the denominator polynomial influence the poles, and the poles give you the modes of your system. So if you kick this system, it's naturally going to want to shake or move according to those modes or according to those poles. So the poles of your transfer function provide you with a lot of insight into how that system or that circuit naturally wants to behave or shake or move. In this case, the system will shake according to the roots of this denominator polynomial, which produce the poles of your system, and that's obviously from this expression going to be connected to the particular values of L, C, and R in that RLC circuit. This now provides you, hopefully, with a way of addressing or starting to approach problems where somebody hands you a circuit and says, provide a transfer function between some particular input and a given output. You now know how to do circuit analysis. It shouldn't be a problem to take the ratio of output to input to determine a transfer function.